Hello, everyone. My name is Hannah. Thank you so much for pulling up to my talk today. As they said, my talk is called Invisible Insight, Strategies for Auto-Instrumenting Go Applications Without Code Changes, which is just a really fancy way of saying, what the heck is auto-instrumentation? Before we go into all that, I just want to take a little bit of time to introduce myself. My name is Hannah. I just graduated from college in 2024, and since then, I've been working at Datadog as a software engineer. So that means that as of today, as of this morning, I have a total of 1 year and 2 days of experience. Thank you. I am very happy to be here at GopherCon. It's my first GopherCon and my first time talking to a crowd this big. So I really hope that I don't panic. Now, if you're wondering what someone with only 1 year and change is doing up here talking to you all, I just want to say that I am actually a professional in the field. I have a Gopher plushie at my desk at work that tells me everything that I need to know about Go. Before we jump into what auto-instrumentation is, I need to first tell you all about what instrumentation is. So to do this, I just want to have you all imagine a website, an application, anything like that. And naturally, when you have something like this, you're going to have users interacting with it, and you're probably going to have some kind of backend, be it a database, some API, whatever. And when you have something like this, you're going to start asking questions. How many users do I have? How long is it taking them to go from point A to point B? What links are they clicking on? And what type of errors are they getting? There's a bunch of unknowns when you have an application like this. And to answer these questions, you're going to have to need something called telemetry. And you all probably know a little bit of what telemetry is, but just to recap, there are 3 main pillars to telemetry. The first one is logs, which defines how or what is happening in your application. Then you have metrics, which tells you how much is happening and how quickly they're happening. And lastly, we have traces, which tells us the how of what is happening. Okay, so now that we've covered all of that, let's talk about what auto-instrumentation is. So again, let's imagine you have an application that you want to learn more about. In order to do all of this, you need telemetry, but it's 2025, is the year of AI, and since half of us are probably vibe coding, we don't want to do things by ourselves. I'm kind of lazy. So what can I do about it? I want to auto-instrument it. And then once I do all that, I can get telemetry, whatever data that I want. So auto-instrumentation is exactly the act of instrumenting your code, getting telemetry like traces and profiles and metrics, without having to make any manual code changes. For the purposes of this talk, I'm going to define 2 different types of auto-instrumentation. The first one is going to be runtime, and the second one is compile time instrumentation. So first, what is runtime auto-instrumentation? As you can probably tell, it happens at runtime. And oftentimes, this will require us to make source code changes. And if you know about Go, it's a statically compiled language, which means that it doesn't do well when we're trying to make source code changes. Okay, so then the other approach is called compile time instrumentation, which happens at compile time. And unlike runtime instrumentation, this will never require us to make source code changes, which means that it works all the time with Go. Now, just because runtime will sometimes require source code changes doesn't mean that every single approach will. And we're going to go over a few examples of both runtime and compile time. Okay, so first, runtime. The main approach that we see in Go is called eBPF, or Extended Berkeley Packet Filter. A few examples are Go BPF, which requires you to use CGo, eBPF, which is owned by Cilium, and the OpenTelemetry auto-instrumentation eBPF library. And the way that eBPF works is by using something called hooking. So first, let's go over what your code might normally look like during runtime. Your code will probably spin up some kind of Go process that will enter the kernel at some point using like a syscall or something like that. And then it's going to do some work in the kernel. What eBPF does is use a hook, in the kernel, which is basically a trigger, and that will act when a certain event happens. And when this hook is triggered, it will divert our process into some eBPF tracing code, which will then produce the telemetry that we want. An example of hooking that you might see is something called binary trampolining, which is basically when you reach a certain address in your code, it will jump you to a different address and then jump you back. And when you jump to a different place, that's when you're calling your eBPF code that will produce all of your traces. Okay. So compile time instrumentation. The first example that I have is Orchestrion, which is a project that my coworkers at Datadog have been working on. And the way that your code will normally work during compile time is that your source code will go through the compiler and then eventually produce an executable, which can be run during runtime. And during compile time, the compiler does a whole bunch of stuff that I'm not going to go over in this presentation because it would probably take me the entire 25 minutes. But a very, very broad overview is that first, it produces something called an AST, or an abstract syntax tree, and intermediate representations, or IRs. These are turned into machine code, and then from there, it's turned into is linked with some other things, and then it produces the executable. Very broad. I encourage anyone who hasn't read up on this to learn more about it because it's very fascinating. So what compile time instrumentation does is, at least in the case of Orchestrion, is use a flag called tool exec whenever you're running a go command. And what this does is that it will attach onto ASTs in your compiler and update them to tag on some instrumentation code. So this will produce your traces and all the other data that you want. And by the time you get to runtime, it will automatically generate some instrumentation code that will now live in your machine code. Okay. So we're getting towards the end of the intro to this presentation. And for the rest of it, I'm going to be talking about how one approach in runtime and one approach in compile time perform and how they compare to each other. So for the purposes of this presentation, I'm going to look at the OpenTelemetry auto-instrumentation eBPF approach. And then for compile time, I'm going to look at Orchestrion. Okay, so the way that I set this up is just a really, really simple HTTP endpoint that communicates with a database. And it's going to do not too much, just going to respond to the endpoint. And I gave it a 1 in 10 chance to throw an error just to try to simulate how things might behave in the real world. In addition, I'm using K6 load testing using 2 different stages. The first one is just an average load test, which will give the endpoint a normal amount of users. And then the second one is going to be spike testing, where I'm going to try to throw as many users at it as I can in an attempt to DDoS it or bring it down. And finally, as we all would be happy to know, we also need to know what our system is doing underneath. So I'm using the Go OS stat package to capture some details about our CPU, the memory, and the uptime of our program. And I can see it, some people are already scanning the QR code. That's just a link to the repo. And if you're interested to see what the setup is like, there's a lot more that I'm not going to cover, but you can go check it out. Just reminder that I'm a 1-year-old gopher. I hope it's not too depressing. So I'm going to repeat this testing and these benchmarks for 4 different scenarios. The first one is with no instrumentation, and I'm calling that my default scenario. And this is just going to be the endpoints in the database with nothing attached on top. Next, I have manual instrumentation, which basically means that I'm using the OpenTelemetry Go SDK to manually create spans and traces to get my telemetry. And then I have 2 auto-instrumentation approaches. The first one is using OpenTelemetry's eBPF approach. So this is going to be our runtime instrumentation. And then next, I have another auto-instrumentation approach using Orchestrion's using Datadog's Orchestrion. And just as a note, I'm using Orchestrion using OpenTelemetry's SDK underneath just to prevent any extra variables when comparing these two, to make it a little bit more apples to apples, as you might say. Okay, so that is, oops, I didn't mean to do all that. So let's look at what things look like. This is just a simple Grafana dashboard, and there's a whole lot on the screen right now, so I'm just gonna go through it real quick. In the top part, I'm looking at the rates that requests are coming in and basically how many are successful versus how many are producing errors. And if you see like funky lines, the code is just running over and over again. So the lines are connecting. So if you look, the default scenario, which has no instrumentation, is producing around 21 errors per second. And this is including both the average load testing and the spike testing. So this is our baseline. And let's see what's running right now. That's Orchestrion. So we can ignore Orchestrion for now. For manual, we're actually getting less errors, which is honestly kind of surprising. This is a live demo. Nothing goes as planned. It's also important to note that the thing that I have written up in the code is a very, very small example. So we can try to extrapolate this to what an application might look like for hundreds or thousands of or millions of users. But this is pretty black boxed, and we'll see what happens. eBPF is still running, so we'll come back to that later. So as you can see, we have a little bit of variance in terms of how many errors we're getting, but it seems that for when we have no instrumentation at all, we're getting a decent number of errors, which is surprising. I'm going to wait for that to rerun in a bit. So let's get back to that. Okay, now we have like some even more crazier diagrams over here. And this is something that makes maybe a little bit more sense to me. You can see that down here, the two bottom, whoa, this is huge. The two bottom sections, here is Orchestrion and here is eBPF. I'm just looking at how long our requests are taking for errors. And these are all P99 stats. So you can see that Orchestrion and eBPF, which is currently running, are behaving in roughly the same way. We're both taking around 32 to 33 milliseconds, and for HTTP is taking around 24 to 25 milliseconds. So not too bad, not too shabby. And this is pretty comparable with the manual instrumentation that I have written up, which also is taking around 33 milliseconds and 27 milliseconds respectively for successful requests and HTTP error requests. And up here, you can see at the very top how our default instrumentation is performing. It's taking around 39 milliseconds, which is a little bit longer, but of course, there's a whole lot of variance. And for HTTP errors, it's taking around 31 milliseconds. So everything is honestly pretty close to each other. We're not seeing a whole lot of overhead when we're introducing Orchestrion eBPF. I'm going to be honest, this is not the results I was getting last night. Yeah, I was really hoping it would be the other way around, but you know how things go with live demos. This was a risky move. But let me just tell you a little bit of what I expected to happen. I expected, and what I was getting last night, was that Orchestrion and eBPF should take longer when hitting requests, just because there's so much overhead with additional work that we're adding during compile time and runtime. And manual instrumentation as well, we're adding a little bit of work, so we want to see more impact on the rates. Let's go back up here. Yeah, that is not what I expected. Let's go back to the presentation. Let's just talk about who wins, and then maybe at the end we'll go back and see if the dashboard is behaving. I'm going to compare the runtime approach and the compile time approach across 4 different categories. The first being performance, then stability, security, and portability, which is just how often can you actually use these approaches. So for performance, as you should have seen in the demo, Both of them are going to add a little bit of overhead, as I said, because you are adding extra work on top of what you're normally doing in your code. So that should be expected. With stability, we're going to see that the compile time approach is a little bit better. With things like eBPF, if you recall earlier, I was talking about about the binary stack and jumping around with trampolining. This requires us to know a little bit about the addresses that we have in the stack, which can be finicky and very brittle. If one address changes, suddenly things are going to fall apart. On the other hand, the toolchain approach does not require anything on a kernel level, which means that things are relatively going to be more stable. And what about security? eBPF requires you to have privileged access to your kernel in order to make the most of its instrumentation approaches, which means that when we have privileged access, a third-party malicious actor could go in there and start messing around with your kernel given the privileged access that you're practically giving it. On the other hand, the toolchain approach does not touch the kernel in any way, which means that it's going to be a little bit more secure than eBPF. And the final sector is portability. And again, the toolchain approach comes out slightly ahead, I would say. With eBPF, you are unfortunately required to have a Linux kernel, which means that all of the graphs that I'm running are running in a Linux kernel or a Linux VM. And I can't run it locally on my Mac. On the other hand, the toolchain approach, again, does not touch the kernel, and all that it requires is that you are able to compile your code, which your code should be doing anyways. The only thing about toolchain adaptation is that it does require you to restart your code and might require you to make some minimal changes to your build process. So if you're looking for something that's 100% hands-off, maybe this isn't the path for you, but it's like 1 or 2 lines. Don't worry about it. So in the end, who's the winner? I'm going to say that they both have their pros and cons. If you have access to a Linux kernel, go ahead and try eBPF. It's great and it's very fascinating. But if you're looking for something that's a little bit more stable and more secure, then try the compile time instrumentation approach. Okay, so what's coming next? Earlier this month, with the Go 125 release, we got something called flight recording, which is basically a process of getting a sliding window of traces. And this will happen continuously as your application is running. And whenever a special event happens, like a panic or anything like that, it's going to return that window to you. So it's basically automatically capturing a window of traces that you can then get at any point. It's auto-instrumentating your code. Next, we have the Go Compile Time Instrumentation SIG, or Special Interest Group. And this is a collaboration between OpenTelemetry, Datadog, and Alibaba to create a compile time instrumentation library that will work for everyone. And they have meetings that happen every Tuesday from 12:30 to 1:30 p.m. EST. So if you're interested at all in learning more about auto instrumentation and where things are going, go ahead and check that out. I do have links up here, but I'll make these slides available later. And finally, the future is still very broad. All of these things that are happening, flight recording, the compile time instrumentation SIG, they're all happening right now. And it's up to all of us at GopherCon and all of the Go communities across the world to continue working on this and see where we can go. A lot of these things are open source. For example, Datadog's Orchestrion. So go ahead, check it out, and maybe I'll see some of your PRs on there. So some final thoughts that I want everyone to take away from this. Instrumentation is super helpful and very, very important. If anyone here is not already instrumenting your code and getting data, please try it out. It's life-changing, honestly, and you have no excuse because it's easy and it's automated. And finally, I want to see everyone working on auto instrumentation because I think it's really cool. So maybe a little selfish of me. Thank you very much. Again, the QR code to the code is up there, and you can find me at any of these places, and I'll be around for the rest of GopherCon. Thank you very much.